Okay, thank you. So I'm Yucheng, and I'm representing my two teammates, Lanyi and Chiang from University of California-Berkeley to present our study. So our study is identifying exoplanets with machine learning methods, a preliminary study. And first, let me have an introduction of the problem space. So the discovery of habitable exoplanets is a hot topic in astronomy. And we can see that exoplanets are planets that are outside the solar system. So identification of a potential habitable exoplanet is a complicated problem. And in this study, we use some machine learning methods to do this identification. And traditional methods, such as the wobble method, and some imaging and gravitational microlensing are expensive, time-consuming, and sensitive to variation in the measurement. So in this study, we proposed the idea of using machine learning methods for exoplanets identification, and we investigate both supervised learning and unsupervised learning. The objective for supervised learning is a three-categorical classification, and the objective for unsupervised learning is clustering. We will introduce later. Yeah, let me first present some related work. Our dataset is from NASA's Kepler mission, and let's talk about its contribution. We first investigate the Kepler mission and its impact on exoplanet identification, and then have some advances in exoplanet science from the Kepler mission. Generally, this mission had collected a large number of data sets, and it collected a lot of characteristics of some potential exoplanets. And because it has very comprehensive data set, so we can use some machine learning-based algorithms in exoplanet discovery based on this data set. And we have investigated some methods of exoplanet discovery with deep learning and some classification models comparison based on the Kepler data. Yeah, these are summarized in our related work. And that is our methodology. First, let's have a description of the dataset. The Kepler dataset is for supervised learning and is collected by Kepler mission, as mentioned before. A total number of more than 9,000 potential exoplanets are included in this dataset. And the features contain characteristics of the exoplanet candidates. And we have some target variable. And the target variable is the existence status of the exoplanet candidate. So if the planet is confirmed as a planet that exists, it is confirmed and labeled as 1. And if it is confirmed not exist, it is labeled as -1 as false positive sample. And if we haven't confirmed its status, it is labeled as 0 as a candidate. So the first dataset is for supervised learning, a three-categorical classification. And the second dataset is for unsupervised learning. This dataset contains confirmed exoplanets, and it has a number of more than 4,000 confirmed exoplanets, and it has very crucial parameters such as radius, mass density, and temperature. So yeah. And before we do the machine learning we first conduct data cleaning. We drop feature columns with large proportion of empty entries, and then fill empty entries with proper values, and do other data cleaning. And we had some exploratory data analysis, EDA, that's correlation analysis, and univariate analysis, and bivariate analysis. For correlation analysis, we plotted the correlation matrices of the Kepler dataset and confirmed the exoplanets set. And from this correlation matrices, we drop some features that are highly dependent on other features to reduce the model complexity and avoid high correlation between features. So the first idea is correlation analysis. Then we do some univariate analysis. For example, figure 2 shows the relationship between the log scale orbital period and target variable. So the x-axis is the log scale orbital periods, and the y-axis is the number of exoplanets. And we can see that the confirmed exoplanets are labeled as red, and the false positive samples are labeled as blue, and potential samples are labeled as green. So from this histogram of the log scale orbital periods of the Kepler dataset, we can find that the confirmed exoplanets follow a Gaussian distribution with respect to the log scale orbital period in the range between -2 and 4. And we also do some various analysis. For example, figure 3 is a star map with RA and DC coordinates. So RA and DC right ascension and declination are just like XY coordinates of the star. So we plotted a star map, and like before, we use blue to indicate the false positive samples, use red to indicate the stars that exist, and use green to indicate the stars that is a potential candidate. And also we have the categorical plot of the log scale orbital period versus number of planets. The number of planets means the number of some planets that's surrounding the exoplanets. For example, the number of planets of Earth is 1 because only one moon is surrounded. Yeah, so figure 4 shows that false positive samples are most likely to have just 1 or 2 planets in their solar system. Oh, sorry. I mean, the number of planets is the number of planets in the solar system. So for Earth, we have, I think, is seven number of planets. Yeah, and just Earth is 8. Yeah, so we can see that if the solar system has very few number of planets, so it's not likely to be a confirmed exoplanet sample. So it's maybe a false positive observation. And then we do feature selection. So we preserve variables with high feature target correlation and low feature correlation. So for example, the first variable is used to just to keep the name of the planet is a Kepler name. For example, Kepler 2022b, like Kepler something like that. And we have some variables, for example, like non-transit flag. This flag means the light curve is not consistent with that of a transiting planet. So yeah, it's one in set, and we have some continuous features, which, for example, like the Kepler period, and it's the orbital period of the Kepler set, and we use its log scale, and also we have Kepler count, number of planets in a solar system, and some radius, mass, and distance. So yeah, this is the features, some examples of preserved features. And we use some methodologies. For example, actually, we first use a linear regression and some basic models. For example, supervised machines as benchmark, and we then use a more complicated method, for example, like classification tree. And it splits data with classification rules based on the highest information gain. And in this model, each internal node represents a sample to be split, and each leaf node represents a class label, a prediction, and we set the minimum number of samples required to split an internal node from 2 to 100, and maximum depth of the tree from 1 to 20. Then we selected parameters with the highest accuracy, and the optimal minimum number of samples required to split an internal node is 53, and maximum depth is 7. This is for classification tree. And then in some mode, classification trees have formed random forest, and it combines multiple decision trees together at training time. So we optimize the number of trees in the forest by setting this parameter from 20 to 1000 with a step size of 20. And we found that the highest accuracy was obtained when the number of trees is 40. And yeah, also we use some naïve Bayes method, and it applies Bayes under the assumption that features are independent. So it's a very simple probabilistic approach to conduct the classification task. And before the training process, we standardize input features. We encode the target variable as a one-hot vector, and we set a prior as the proportion of each class in the sample space. Yeah, and before this pre-process, we run naïve Bayes. It's a very famous method classifier, right? And then we use some neural network. It's another machine learning model. It's widely used in classification problems. We try 3 activation functions: logistic, tank, and ReLU. And we also choose 3 types of solvers: stochastic, gradient descent. We use quasi-Newton method and add-on optimizer. And we optimize the layer size and learning rate. We obtain the optimal neural network, use 10 as activation function, and add them as optimizer with a layer size of 25 and a learning rate of 0.3. Yeah. And for the clustering, subproblem, we use k-means. So it's a classic unsupervised learning algorithm for clustering problems. It partitions data into k clusters with the objective of minimizing the sum of distance of each sample to the cluster centroid in a repeated manner. And we aim at finding out which exoplanets are in the same group as the Earth and might indicate potentially habitable places for human beings. So next we talk about experimental results and our analysis. And for the classification, 3-category classification, we found that classification tree achieves an accuracy of more than 99%, and random forest achieves an accuracy of more than 99%. 92%, and naive is nearly 90%, and neural network is more than 99%. And we first evaluated the performance of these models with cross-validation. We use actually K4 cross-validation. We can use 5, we can use 10, and we use 10 for cross-validation. For cross-validation, the random forest model achieved the best average accuracy of 82%. And we also visualized the classification tree with the highest accuracy. Yeah, figure 5 just show the optimal decision tree. And in addition, we plotted the importance value of each feature. This is measured by Gini importance. Yeah, table 2 just shows the Kepler feature list with variable name, importance, meaning, and description. And for example, the variable KOIFP flag SS, its importance is 0.3, and its stellar eclipse is a flag. One means some phenomena caused by an eclipse in binary observed. So it's just a flag. And we also have some continuous variable, for example, KOI period. So as we describe its orbital period measured in days, and it's taken in the log scale. Yeah, and we have also have like transition epoch. Yeah, especially in BJD and some other features with importance. And for the classification problem, we visualized the exoplanets in the same cluster as the Earth in a star map measured with rate ascension RA and the declination DC. Yeah, so these are all confirmed exoplanets. On the top left side is Earth, and we have found other exoplanets on this map. For example, HD 17156b. For example, some other exoplanets confirmed are classified as the same cluster as Earth. So conclusion, future work. So we in this preliminary study, we implemented machine learning methods for two subproblems. One is regression of three-categorical regression, and another is a unsupervised learning, a clustering problem. And for future work, it might be interesting to create new features from the current feature set using feature engineering techniques, because they can be helpful to improve model performance. And in addition, we can investigate the receiver operation characteristics, RSA, and the precision factors to understand the diagnostic ability of different machine learning models. And for example, McNamara's test can also be applied to compare different algorithms. And finally, the discussion of statistical significance test and execution time can be included in the modeling evaluation. And we can apply a more complicated model in the future. Okay, that's all. Thank you. Yeah, and Q&A. Yeah, it's the next. Part. Thank you. Thank you very much.
Thank you.
Do you have questions?
Thank you very much, Mr. Yucheng Jin. The presentation is wonderful. Does anyone have any question? Are there any questions from forum? I think there is no question. Thank you very much. But I have one question, Mr. Yu.
Okay.
If you don't mind, can you explain the experimental setup, please? So what kind of software did you use and what are the parameters?
Oh, yeah. We use scikit-learn. Yeah, we use scikit-learn scikit-learn regressors, and the parameters, for example, I have, sorry, just yeah, we use scikit-learn library from Python, and we can see that we for example, parameters of the classification tree is the maximum depth of the tree and the minimum number of samples. So we for the tree, we just adjust these two parameters. For random forest, based on the tree, because we have obtained a tree. So for random forest, we optimize the number of trees in the forest. And for naive Bayes, we just set up the prior and process the input as one hot vector and standardize it. And for neural network, we optimize the parameters of activation functions and solvers and layer size and learning rate. And these are all realized by scikit-learn. Scikit-learn is very famous for machine learning in Python.
Yep. Thank you,
Thank
Jin.
you.
Wonderful. Thanks a lot.
Thank you.
Yep. Best wishes for your future research.